Okay, let's start today's class while others are still joining. Today, we are going to continue our discussion on 8051. Yesterday, we had seen how different memories are available and basically what are the memories available in general that are useful for embedded systems. And also, we started with the pin configuration of 8051 or 89S51 specifically. So while other students are joining, so I'll show you certain things before we continue our discussion from yesterday's class. So I'm going to turn on the camera and then I'll show you some real embedded systems. I'm sure many of you must have worked on embedded system to the capacity as a hobby or for some projects. And if not, that's also fine. So I'm going to show you some circuit boards, some hardware pieces that are available for research purpose or for embedded system development in general by using microcontrollers. Okay, so I'm sharing the camera. Okay. Can you see this? Can you see me? Okay. I'm going to show you two or three boards that are used for different applications such as using a microcontroller. So if you look at this, let me control the lighting. Okay. If you look at this particular board, this is a typical embedded system that has been developed around a microcontroller chip. So this is the 40-pin chip, which is 89S52. So yesterday we were looking at 89S51. So this is the similar chip, but with some added facilities. So this is 89S52, which is a 40-pin integrated circuit. So you can see pins on both sides, on the basically on the left and the right. It's pin number 1, so that is this side. First pin on the top is pin number 1, then 2 3 4 5 up to 20, then this is 21, and then it goes till 40 on the upper right. So 1 and 40 are side by side, basically on left and the right side. So this is the microcontroller, and since I was telling about an embedded board, so this embedded system board has been developed around this microcontroller, but it has several peripherals and memory devices. So first of all, I don't see any memory chip external to this microcontroller. So that means whatever memory is there, it's inside this particular chip. But you can see lots of components are here. So first of all, this is the LCD. I think you can easily recognize this by now because you are all third-year students. So you are becoming experts gradually. So this is a liquid crystal display. So this is 16 into 2. That means there are 2 lines, but 16 characters can be displayed side by side. So there are 32 characters can be displayed, up to 32 characters can be displayed over here. So this LCD has a bunch of pins. So these are interfacing pins for connecting the LCD module, and these pins are actually going to the microcontroller or through some intermediate chips and then microcontroller. And also power supply pins are available. So you can see the pin configuration separately. But more importantly, there is a real-time clock chip. So this is a RTC chip, real-time clock. This RTC chip actually counts time in something like a simple clock, but without a display. So this is the electronic chip which sits behind the display. So the clock will come on the display, and so the time will be displayed on the screen, but the time is actually measured or counted inside this particular chip. But this particular chip is quite small. So this is I think the number is DS1307. So this is one of the peripheral chips which is interfaced through one of the serial communication protocols from the microcontroller. So basically it is connected by using some serial input output pin with the microcontroller. But this pin is using a crystal. You can see there is a little crystal over here. So this is this shiny thing, cylindrical thing. So this crystal is that time base for this particular clock. Whereas yesterday we discussed about external 1 and 2. So the external 1 and 2, which are the microcontroller pins, are connected to this external crystal over here. So you can see the crystal, which is another shiny thing, but of a different frequency. This is some 11.0592 megahertz, whereas the other crystal is just 32.768 kilohertz. So this is in kilohertz, but this is in megahertz. Okay, so the microcontroller's clock runs at 11.0592, which is the frequency of the crystal. But crystal also requires extra capacitors. With the actual hardware circuit, I will explain to you later why these capacitors are necessary. So this crystal and the capacitors are connected to external 1 and 2. If you look at the pin configuration of this 89S52 or 51, even same thing, or similar thing. And then there is a circuit inside the chip, inside the microcontroller, which is the oscillator. So that means it generates the clock signal. So with respect to the circuit and the external crystal and the capacitors. In addition, you can see some other components, such as this is the power supply regulator. So this is this chip with the black thing at the back is a voltage regulator. This is an integrated circuit voltage regulator, which gives 5-volt output, and 5-volt goes to LCD, microcontroller, and all other chips, okay, on this board. And in addition, there's a power connector here, something like a power jack is there, so you can plug in an external power supply here. And this is a power on-off switch. Then there is a buzzer over here which gives beep sound, and then there is a capacitor which is a part of the decoupling capacitor. It's called decoupling capacitor for the voltage regulator. So decoupling capacitors are also present in the smaller values, so which are very close to the voltage regulator over in this space. On the other side, you can see there is a serial port connector. So this is a serial port connector, and this serial port connector is connected to this chip, which is a level translator chip. So this is basically the chip that is connected in between. So this is converting the voltage levels for RS-232. RS-232 is the protocol which was available in older PCs. So this is a bit older microcontroller board. So that's why you get to see this 9 pins D connector, and this 9-pin D connector operates at plus minus 9 volt for logic 0 and 1. So logic 0 means plus 9 volt and logic 1 means minus 9 volt. But here this voltage regulator is a single supply voltage, so that is 0 volt and 5 volt are provided as power supply. You need that minus and plus voltages which are beyond higher. Plus 9 is obviously higher than 5, and minus 9 is definitely not present. So it actually converts, it takes 5 volt and converts those two into plus 9 and minus 9 volt. And whenever the communication happens, it actually sits in between the microcontroller and this particular pin connector, and this chip acts like an interface. I will come to this details of this kind of chips later, while we will consider UART communication. Okay, and in addition, all the pins, like the port pins, port 0, 1, 2 and 3, so all the port pins are available as connectors on the board, and these connectors or the pins for this from these connectors can be tapped for connecting any external chips apart from whatever is present on this board. In addition, there are some switches and there are some light emitting diodes, and also jumpers to disconnect certain portions. And also finally, this is the programming connector. This is in-system programming connector. So you can just have to plug in an external cable to a computer, and then this will give this will help to program the flash memory, the non-volatile memory inside the microcontroller. So I think I left one thing, which is the simple battery. So this is a coin battery connector, which is absent over here. The battery is absent over here. The connector is there. You can put this coin cell over here in order to run the RTC, the real-time clock. So the clock should be turned on even if you don't have the 5-volt power supply. So clock should be always on. For that, you need an extra battery over here, such that it will keep on counting. But whenever you apply power supply, then the microcontroller can read and display it on the LCD display. So this is a typical embedded system board that uses 89S52. But you can claim that people who have used Arduino or Raspberry Pi kind of boards, those are much more advanced as compared to this particular board. Now I'll tell you how to customize, or basically how a customized board look like. This looks like a general purpose microcontroller board, which has lots of pins, all quite big in size also. So we are actually developing another board at IIT Kharagpur, which is our own development. So you can see the board over here. If you look at it carefully, some IIT Kharagpur is written, IIT KGP is written somewhere. And this is based on MSP 430 microcontroller, which is an ultra low power microcontroller, much lower power than even AVR microcontrollers or Atmega microcontrollers. So this is, if you see this chip over here, wherever I'm touching with my pen, so this is the microcontroller chip, and this is just 5 mm by 5 mm. Okay, so the size of the IC is just 5 mm by 5 mm, whereas in the previous case, the size of the chip was in inches, several tens or close to several inches. Okay, but here it is very, very small. In addition, this board has a Bluetooth module over here. So this is BLE5 module, Bluetooth Low Energy 5 module, which is an ultra low power Bluetooth communication device. You can connect this board to your smartphone and look at the readings that this board is doing or taking. So for what is the purpose of this board? The purpose of this board is to assess the quality of water. So this microcontroller system has been developed to customize it for water quality analysis. Okay, for that to happen, we actually placed several chips over here and the LEDs. So there are LEDs, white LED, which is the white one, and there is a red, green, blue LED, RGB LED over here, which is very small. I'm not sure whether it is easily visible or not. So the RGB LED is this one, and white LED is this one, and in between those both the LEDs, so that means there are 4 LEDs over here, 3 over here, and 1 over here. So white and red, green, blue, and in between those 2 LEDs there is an optical sensor. Okay, so this optical sensor measures the reflected beam of light from the water sample, and then it actually gives the data to the microcontroller. Then microcontroller assess the data and find out what is the quality of water based on certain analytical measurements. Okay, so these are optical and measurements that could be done. And in addition, there are 2 channels. So there is a channel, I think channel 0 and channel 1. So 2 channels of independent measurements could be done. And then there are some intermediate chips. So these are for driving the LEDs and also taking the readout from the sensor, optical sensor. So this is a water quality sensor board. But more interestingly, on the back side of this board, we have connected a little solar panel. So you must have seen large solar panels, but this is just a centimeter scale solar panel. Even smaller panels are available in the international market. It's not available easily in India, but it's available elsewhere outside India. So we got one of the solar modules, solar panels, and this solar panel harvests energy, and that means this device is totally battery free. So this entire PCB will do water quality measurement forever. You can deploy it in rural area, for example, and then it will keep on measuring, harvesting energy from solar radiation, and then utilize that energy for running microcontroller, Bluetooth, and even it has USB connectivity if necessary. You want to do USB connection. But you can see one connector here, one connector over here, 4-pin connector. So this connector is for programming the microcontroller. So this is basically in-system programming connector. Okay, so these are the 2 examples that I wanted to tell you. This is how we develop embedded systems, and those embedded systems should be customized. If you understand the basics, then you can always work on it and then obviously improve the features. But I'll now tell you I'll show you something which is very state of the art, something internationally very much recognized and very state of the art. That is very modern kind of microcontroller circuit. Okay, so this is another, this is my own work actually. So I'll just remove possibly. Okay. So this was my work that I did earlier. So you can see the size of the PCB, which is even small. It is comparable to my nail size. You can compare actually directly from here. And more interestingly, where is the microcontroller? So this board is having chips. This is a huge high density arrangement of all the components on both the sides. So it's a very high density printed circuit board with so many chips along with the microcontroller. Now, I'll show you something. This board is a flex PCB board. Okay, so that means I can actually flex it. So this is a microcontroller board along with lots of other components, which you can flex it like paper. You must have seen the connectors made of this kind of PCBs, but I'm not sure whether you have seen the full PCB out of it. Now, what is the purpose of this PCB? I'll tell you after explaining very briefly about what it does. Basically what it contains. So this is the microcontroller. So this microcontroller has basically all that flash, RAM, everything inside. And then all the components around are for multiple purposes. One of the purposes is energy harvesting. So it can harvest energy from a coil which could be nearby, or an RF energy harvesting. Suppose you are running Wi-Fi and all other mobile devices around, so it can actually harvest energy from those ambient RF energy which is available in our office or home space. But after harvesting energy, it can actually store a little bit of energy in the capacitors that it uses, and after that, this entire device is supposed to be placed inside the body, something inside the hand or inside the brain of an individual for treatment of diseases. So this is a bioelectronic circuit or bioelectronic embedded system by using a microcontroller, ultra low power microcontroller, which can be used for treatment of diseases such as Parkinson's disease or epilepsy, or even different types of paralysis. Even stroke patients can be using such devices if they have paralysis at some part of the body. So this device was actually, you can see it's a very lightweight, very thin, and it is flexible. So if you put it in the body, so even if you flex it, you just bit of assault or basically treat it not so badly, then it will stay for even more than 10 years supposedly. We have tested this on rats. Okay, so inside rats and monkeys also. So I have personally tested this earlier, and this is my own design of an embedded system by using a microcontroller. So you can even make it even smaller for implantation in the body. But for that, you can replace all the components that you get to see over here by using an integrated circuit design, a single chip design. But single chip design of such a very powerful circuit is very difficult, or rather it sometimes may not be possible. At least all the features may not be integrated very easily. So this is how actually, so I just wanted to tell you that what are some of the possibilities of embedded systems that you can use. I can also show you some other devices, but this uses ferroelectric RAM, in FERAM or NVRAM that I explained. This is some project under development which is not completed. That's why you get to see this 3D printed box here. And this is the microcontroller which has the FERAM or ferroelectric RAM or non-volatile RAM, NVRAM, that we discussed. Okay, so and it has if you look at the other side of this board, there are lots of sensors, and these are mainly gas sensors, different types of gas sensors. Some are electrochemical gas sensors, some are resistive gas sensors. You may not go in detail, but more importantly, what I'm saying that it can measure temperature, humidity, different gases by using a microcontroller, and also it communicates to the basically remote mobile phone, or you can upload data to the cloud through a Bluetooth interface through the mobile phone. So such devices you can actually develop, and we keep on developing such projects. So there are many such projects at IIT Kharagpur, even in other departments sometimes. So you will find that you can have lots of scope if you take the basic concepts properly. There is a lot of scope that you can actually explore. So I wanted to motivate you basically. So that's the objective of showing all these devices. So if you understand the basics, if you get yourself motivated, you can really work on fantastic, basically, kind of projects that are possible through this knowledge. So obviously you have to go through the basics first. So these are all fancy circuits which came up after several iterations, many years of work. It doesn't come very easily, right? These are not directly available, or the codes need to be developed. The hardware needs to be redesigned many times and iterated such that it performs as we want it to perform. Okay, so with that, actually, so I'll continue to the portion where we left out last time. So do you have any question on this that I just showed? Okay, so since there is no question, so I'll go back to the previous point where we left out. So I'm sharing my screen. Okay, can you see my screen?
Yes, sir.
Okay. So here, yesterday we started with 89S51. So 89 or anything 51 series. This is an MCS 51 series. So we have seen the microcontroller series 51 device or microcontroller device having 4 kilobytes of in-system programmable flash. We had already seen this. But the first thing, the board that I showed you is 89S52. So the board that I showed you today is 89S52. So 51 and 52 are very close by. So it is again a MCS51 product or MCS51 microcontroller. But 52, this particular 52 microcontroller has certain small changes. Like instead of 2, there are 3 timers. Instead of, I think, 4 or whatever. So there it has more interrupt sources, and it has some extra features such as 8 kilobyte of flash instead of 4 kilobyte. So there are small differences in the board that I showed you today. But we'll continue with 89S51 because it is pretty similar to 8051. Okay, and we should cover 805. So we ended with the pin configuration discussion on the pin configuration last time. So this is a plastic dual inline package. So it looks exactly the same that I had shown you in the first PCB or printed circuit board. So all the 40 pins are distributed into 4 ports and power supply, and then there are some control lines. So one thing that we skipped yesterday due to time, which is reset. So reset is about resetting the microcontroller or resetting the program counter to start from the beginning. It's like a system reset in your desktop PCs. Okay, so this reset is a signal which is an input signal to the microcontroller. If you apply a reset signal, this microcontroller will start executing the program right from the beginning. That means 0, 0, 0, 0 in the memory map. If you remember, we had seen a memory map for microcontroller, and that memory map 0, 0, 0, 0 will be executed if you are using this particular reset signal. So I'm talking about this. So after reset, your program counter will be reset to this particular value as an address. In addition, if there are other things which needs to be reconfigured at startup, so those things such as flags can be reset, registers may or may not be reset. So all those initial settings comes into place after the reset signal is pressed or reset signal is applied from outside. So there is no bar, that means it is active high. So logic 1 will reset the chip, logic 0 will remove the reset. So during normal operation, your reset signal should be kept at logic 0. Otherwise, your microcontroller cannot execute any program. You have to release the reset signal from outside. So this reset is an external signal. Now, this is more important or rather equally important as the pin diagram, but the level of details that are there in this block diagram is significantly high. So we'll spend some time over here to understand what is there inside the microcontroller. So this block diagram represents different circuit blocks inside the microcontroller. So initially I told you that microcontroller means okay, I'll just close the slide. Initially, I told you through the previous slide that microcontroller has three things mainly: microprocessor, some memories, and input-output ports, and internal buses, data address, as well as control buses. Also, we have seen control buses in one of the slides. Okay, so now we will try to find where are these blocks inside that complex, relatively complex block diagram over here. Now you can see over here in this particular block diagram, there are different blocks. I will just zoom out a bit. Okay, so this is the total block diagram view, and we will try to identify where is the microprocessor, where is the memory. I think memory is easy to identify, and where are the I/O ports. First, the microprocessor. Where is the microprocessor? So microprocessor is mostly towards the middle of this block. So this is the total microcontroller, but they don't have any, they are not showing any boundary for the microprocessor. So microprocessor needs to be identified over here. The first thing to identify where is the microprocessor is ALU. Look at ALU and look at the circuits or blocks around arithmetic and logic unit. So ALU is definitely within the microprocessor part, that is MCS51 microprocessor here, and ALU requires two inputs. So ALU two inputs are coming for temp1 and temp2. These are actually temporary resistor TMP1 and TMP2. So these temporary resistors are the two inputs, are serving as two inputs. So this each resistor is each resistor is only 8 bits, because this microcontroller has 8-bit ALU. Except for certain functions, the ALU performs 16-bit operation, but only it takes 8-bit operation, completes it, then it takes next 8-bit and then completes that. Then it merges the data by some other blocks, and as a result, you can get total 16-bit operation if at all you need 16-bit. So for very few instructions, it will only perform 16-bit, but for most of the instruction, it will do only 8-bit arithmetic and logic operations through this ALU. So ALU is identified TMP1 and TMP2. These are registers, but inside the microprocessor part of the this chip. Then register B, you can see, and then ACC. ACC means accumulator. Okay, so it is equivalent to register A. So the register B and register A are the two registers apart from TMP1 and TMP2. So already we have identified 4 registers, temporary registers 1 and 2, then accumulator. So it is the nickname to register A, accumulator, and register B. So that is one. This 4 registers ALU. Now another thing that is a part of the microprocessor is stack pointer. We'll come to this slightly later. Okay, let's look at the other side of the ALU. So the ALU is connected to PSW. PSW means program status word. Program status word. So PSW is another name of flag register. So we had seen the generic architecture of the microprocessor in this. So we had seen that ALU is connected with the flag registers next to it. So flags have either, it indicates whether you have a carry or not, answer is 0 or not, parity is odd or even. So some similar kind of indications are there in the flag registers. So some microcontroller or some microprocessor call it a flag, some other call it program status word. So this is a flag register. Other parts of the microprocessor in MCS51 is instruction register and timing and control. Okay, so these two blocks are definitely the part of the microprocessor. You can see instruction register and timing and control. Okay, so instruction decoder is obviously there, but it is not explicitly shown, because if you have instruction register, there must be some decoding. So they are thinking that decoder is so obvious not to show it separately, but decoder is definitely there. Okay, so this things are the timing and control and instruction register are also part of microprocessor. Then interrupt, serial ports, and timer blocks. This is not the part of microprocessor. This is a part of input output. Okay, so we'll talk about it later. Now coming to this stack pointer. So this stack pointer is important because the stack pointer actually what is a stack? So if you have a stack of books, that means you have multiple books on top, kept on top of each other. Okay, so that is a stack of books. Now stack pointer is a register. It's a specialized register. It's like something similar to B, A, or TMP registers. But this register is a 16-bit register. So these are TMP1 to A and B are 8-bit registers, whereas stack pointer is a specialized 16-bit register. And this 16-bit register actually points to the top of stack, TOS, top of stack. Again, while studying programs or programming part of 8051, we'll study TOS, top of stack. So that is basically, so some data is there in the RAM, and that RAM, certain area of the RAM is actually pointed by the stack pointer. Another thing in the microprocessor, what we expect is this program counter. So far in the microprocessor, we have identified flags, ALU, instruction register, timing and control, and register A, B, and so on. But program counter is something that we need to find out. So this program address register and PC incrementer, program counter incrementer, and this program counter. So these three things, program address register, PC incrementer. So this is basically up counter. Incrementer means up counter, and then program counter itself. So this is a register. So in this case, so they are splitting the program counter into multiple sub blocks. That's why you get to see 3 blocks over here. So program counter is actually, it's a 16-bit register similar to stack pointer, but in addition you have to increase it and then keep it back. So that's why you need an up counter, which is a PC program counter incrementer. So you can say this is a misnomer. So program counter is the name of a register. It's not actually a counter. So the counter is actually present over here in the incrementer. And then program address registers. Obviously, there are pins showing out the address lines to the external world. So for that to happen, so there is an address register. So that means once you have the program counter some data, it copies the value and then puts it in another register, such that program counter can be incremented separately while something else is getting addressed externally through the pins. Okay, and now so register A, B, TMP1, 2, stack pointer, ALU, this PSW, program status word, interrupts, no, not interrupt, instruction register, timing and control, and then PC incrementer, and program address register. These are the microprocessor part of this particular diagram, of the original diagram that we considered. Microprocessor has been identified. Now memories. I think it's very simple. Memories are located over here. So RAM address register and RAM. So these two combined together. So this is a static RAM. This RAM is the static RAM, and its register control or its address registers are the part of the RAM chip also. So part of the memory system actually. So and also the flash part. So flash is for code storage and RAM is for data storage. Okay, and this is static RAM, and this flash RAM and this address registers with this memory are the memory subblock for this generic diagram. Now input output ports. So whatever remains after this identification are the part of IO ports. Everything, in fact, everything else, whatever that we have not covered, such as port 0 driver, port 2 drivers. Okay, so these drivers means what? These are simple buffers. Buffer in digital electronics, buffers means it's a cascade of 2 inverters. So what is a NOT gate? NOT gate will give input is opposite in logic at the output for a NOT gate. But if you cascade 2 NOT gates in series, okay, or one after another, so what will happen? So the input equal to output. Okay, if you cascade 2 NOT gates in series, so each pin or each line, like port 0.0 might have 1 NOT gate, port 0.1 might have another NOT gate. Obviously, port 0 has some specialty. I will talk about that later on. But assume that every pin over here, for all the pins, are having drivers, like port 1 and port 3 also have drivers. Port 0 and port 2 are also having similar drivers. So drivers means cascading of 2 NOT gates for each of those lines are there. Why do we need 2 NOT gates in series? You can ask me why we are putting some extra circuit which is not necessary. Directly connect all the 8 lines, 8 pins to the output. So we will discuss that with the actual circuit, MOSFET level circuit inside this drivers separately. So drivers are part of the external interface, but IO port is actually mainly depends on these latches. So these are some sort of D flip-flops. For every port pin, so there is a latch. That means a D flip-flop for each and every line, or every port 0.0 channel must have a latch, port 0.1 must have a latch, and so on for all other port pins. Okay, so each port latch means port 0 latch means there are 8 latches. That means there are 8 D flip-flop like circuits, okay, or RS flip-flop like circuits, you can assume. So typically it is D flip-flop like circuits are more preferred. And then port 2 also have 8 latches or 8-bit latch. Similarly, port 3 latch and port 1 latch are present. So all these are all 8-bit latches each. So that means 8 into 4, that is 32 IO lines, input output lines are available. So first the microprocessor communicates to the latches, and whatever is there in the latch, it gets communicated to the driver. But look at the direction of these lines, all the lines, these are bidirectional lines. Means that means signal can come in also, not just so latch, you are latching something and then the output will be available at the port pin to the external world. But if something comes from outside, then also it latches. So that means this is not simple delatch, it is a bidirectional kind of latch. That means you can latch in both those directions. Okay, so you can latch the output direction, like something from microprocessor to the external pins, or other way around, from something from the external pins and going to the microprocessor. So bidirectional latches are present. Okay, and also in system programming port, ISP port is available. So this ISP port is a part of port 1 driver. And then you have this watchdog timer. So we had discussed this specialized timer. Yeah, question.
Sir, who gives the clock to these latches? Is it like the
timing and like? So the timing and control basically takes the master clock signal from the oscillator. So this is just a simple crystal oscillator. So basically some feedback circuit along with an inverter. This is a digital circuit. So there is some digital oscillator which gives a square wave at the output, and this square wave is distributed by this timing and control. So whenever each of those blocks, wherever you need, like for latches like D flip-flop, you need a clock signal. So that clock signal is not deliberately shown here, but it is controlled from timing and control. So this timing and control is the one of the heart of the system, actually, you can say.
Okay, because I had like probably not the right time to ask this doubt, that how will the interrupts then happen automatically if it's latched by something by the MCU itself?
I will discuss that while doing the interrupts. Okay, so remind me this question if I forget. Please remind while the interrupts will be covered. So I'll come to this question, that how this clock is actually influencing interrupts even actually. So it's a type of, there are two types of interrupts basically, rather there are two types of data input if you want to learn at this point in brief. So one is interrupt based data transfer, other one is polling based data transfer. So you can do software polling, and or you can just wait for the interrupt. So whenever interrupt comes, so this clock is always available to the interrupt if you enable the interrupt. So your time resolution is 1 clock cycle at least. So that is the minimum time that must be required to identify an interrupt.
Yeah, I got that now. Yeah, the question's clear.
Okay, good. Now, so this program logic, is a bit fuzzy. Device. So ISP port, in system programming port, basically takes the serial data. This is the serial data in SPI format. Again, this is a new term. If you look at the pin configuration, this alternate function MOSI, MISO, and SCK. This means master output, slave input, master input, slave output, and serial clock. So these three Actually, these names came from a serial port, a synchronous serial port called Serial Peripheral Interface, SPI. But actually, this microcontroller doesn't support SPI in general, but these three pins, SPI-like pins, are used for programming, for in-system programming purpose only. And for that, actually, this is a serial kind of port. It is different it is actually different than this RxD, TXD that you get to see here. So this is an asynchronous serial port, and this is a synchronous. Synchronous means there is a clock associated, but asynchronous means the clock is internal. Okay, clock is also associated here, but it is internal. So the synchronous serial port, that means you can change the clock from outside and change the control speed of communication here. But for this asynchronous one, the speed of communication is fixed once you program the microcontroller. Okay, so for this serial port, MOSI, MISO, and SCK, so those pins are part of port 1. So that's why this ISP port is connected to port 1. And ISP means in-system programming port. And then once the ISP gets that serial data, it actually communicates to the bus, and then it actually gets programmed in the flash. But there is a program logic which is also connected to this EA VPP along with the timing and control. So all the arrows and lines are not shown, to be very frank. Over here, this program logic, each and every block is controlled by timing and control. Over here, each and every block is having some control or some influence from the timing and control. So this program logic basically, it does what? It actually takes in that high voltage that I was discussing yesterday. So you have to basically apply high voltage to the special type of transistors, which are not normal MOSFETs, but these are special MOSFETs with charge traps. So I explained the name about FN tunneling yesterday, which is you will possibly study that in VLSI engineering, Fowler-Nordheim tunneling. So these are basically, that's the physics behind the special transistors that store certain charge, and then if you store the charge even after power off, that means you are acting as a you are making the transistor a memory transistor. Okay, so that is a very brief explanation how flash works, but you can refer to that separately in VLSI engineering, or you can ask me separately during doubt clearing session. I can tell you the entire story or in relatively more detail. Okay, so program logic is basically mainly, it's also a part of IO, I will say, or it's an interface between the microprocessor and the IO to update the flash. If you want to erase the flash and update with new program, in that case ISP port and program logic comes into picture. And then Watchdog Timer is a special timer, as we briefly discussed, that it keeps track that if the program is hanging or not, if the operation is actually going as per certain time specifications, such as every few milliseconds, Watchdog Timer tries to reset the microcontroller. So that's the main purpose. So Watchdog Timer actually gives a signal. It's like a barking of a dog every few minutes or every few seconds. So instead, every few milliseconds, Watchdog Timer gives a signal to the timing and control, and as a result, it tries to reset everything. So it's an internal reset after every few milliseconds. But ideally, we don't want that all the time. Sometimes it is good for safety. If it hangs, it will automatically come out of the hanging state and start from the scratch. But you can disable the Watchdog Timer. You can actually enable it if necessary. And from the upper side, I think we have covered each and every block over here. So I think you must have understood what are the blocks corresponding to this processor, memory, and ports, input-output ports. So any question up to this point? So which one I left out? Can you point out?
Can you repeat what you told us about flash and program address register?
Program address register. Okay. See, the program address register basically used for both the purposes. I only explained you about the normal execution of the program with the program counter and the incrementer. But program counter, PC program counter, incrementer, and the address must be applied to the flash memory locations during programming purpose also. So program logic is also tied up, or rather timing and control is tied up to all the necessary blocks. So timing and control is like a big boss. So this boss is sitting at some place and controlling each and every operation by controlling the signals, and also by control the timing pattern, basically the timing waveforms that we had seen earlier in one of the slides, that you had seen this timing diagram. So this is an external timing diagram. So all these pins are outside the microcontroller. But the timing diagram inside the microcontroller is actually much more complex, or relatively complex. And that means this timing and control actually applies timed clock signal, or timed read signal, timed write signal to different blocks. And so while programming, so timing and control senses if you are applying high voltage, that means you are not operating the microcontroller in normal execution mode. So that's first indication. So what it will do, it will enable Isp port automatically. It will enable the program logic. Basically, program logic means what? It is basically a little offshoot, or little assistant to this timing and control during the flash programming process. So during flash programming process, you have to apply your timing becomes slower. So this timing from the oscillator is in megahertz, but during programming it comes to kilohertz. So programming process is always slower. So you can actually download something from internet, so you can see that the speed is basically sometimes is actually slower. Why it is happening? Because while downloading, you are also storing it in a memory, and while storing in non-volatile memory like solid state disk, it takes very little time. But while storing in hard disk like older memories, obviously it takes relatively longer time. So flash is quite modern memory, but it still takes more time to write and less time to read. So during read, basically program execution, flash is very fast, access very fast. But this program logic essentially controls the timing if necessary, and also the signals that goes to the flash. So this diagram, again I'm telling, this diagram is not a complete diagram. So the complete diagram is not possible within one page. It should be a very large diagram. So program logic essentially controls necessary timing during the writing process or erasing process of the flash. Is that clear, or if you were asking something else?
I got it, sir.
Oh, great. So regarding the interrupt, serial port, and timer blocks, so we have not discussed this thing in detail. I think each of these things are having its own internal block diagrams. So this block is actually a hybrid block having multiple block diagrams within itself. So interrupt structure consists of software interrupt and hardware interrupt. Serial port, there is UART port. So this serial port only refers to RxD TXD lines for UART, or universal asynchronous receiver transmitter communication. So MOSI, MISO, so that is related to ISP. That's not this serial port. And then there are timer blocks. So the timer / counter blocks, in fact, timer 1 and timer 2, or sorry, timer 0 and timer 1. So these are the two timer blocks in ATS51. If you go to timer ATS52, there are 3 timers over here instead of 2. So another thing I missed out is this buffer. Okay, so this buffer is again similar to this kind of drivers, but instead of and this buffer is again a bidirectional kind of NOT gate arrangement. That means there are 2 NOT gates looking outside, and 2 NOT gates looking left to right, and 2 other NOT gates looking right to left for each of the pins. So here this is 8-pin buffer. See, the point is this port pins are 1 pin outside, but whenever you see this kind of line over here inside, obviously each line is actually part of the bus over here. So there are little small buses that are present, which are quite local sometimes and quite global sometimes. Okay, so this buffer is similar to the drivers, where it is trying to avoid loading. So the purpose of these drivers and buffers is pretty much the same. So although they are calling it differently for the port pins and internal buffering, so the purpose is that buffer actually prevents loading of the digital circuits while they are connected. Now, what do I mean by loading over here? Loading, recall what is fan out in digital circuits. In fan out means how many number of inputs of similar gates can be connected in parallel to output of one gate, one logic gate. Okay, so look at the definition, revise it. Fan out means basically there should be a maximum limit up to which I can load the output of one of the gates. Why that maximum limit exists? Because all digital circuits are analog in nature. If you connect lots of inputs of other logic gates to the output of one logic gate, so due to loading, so the input impedance reduces for if you connect multiple gates in parallel. And now reduced impedance is connected to the output of the first gate. Okay, so if you do that, then the first gate actually cannot supply adequate current because it has also finite output impedance of the first gate. So you have to match the impedances, okay, for best performance. So in digital electronics also impedance matching is necessary. And in simple terms, you have to avoid loading. If you connect 100 gates to one of the lines, then it may not stay at logic 1. If you are maintaining, if you need to be at logic 1, it can come down, the voltage will come down, so it can enter into the noise margin, and as a result your result will be wrong, or your logic level will be wrongly interpreted by the second stage gates, where 100 gates are connected in parallel at the input, any one of the inputs or multiple inputs. So this is for avoiding the loading effect. Now look at one thing. Where are the address lines, address bus, data bus, and control bus? So that point is still missing. Look over here, port 0 are acting as address as well as data, AD. Port 2 is acting as, or alternate function could be only address. Okay. Now let's try to correlate this pin configuration with the block diagram. Port 2 and port 1, port 0. Port 2 and port 0, right? So port 0 is address data. So remember this, and port 2 is only address. So if you consider that, here also you'll find port 0 and port 2 side by side, because port 0 is having alternate function. Each pin is having alternate function as address or data. How do you connect that? For address, something should come from the program address register, okay, or program counter through this program address register. And for data, something should come from the data bus. So this internal line is an 8-bit data bus, okay, and this 8-bit data bus is connected to almost everything inside this particular microcontroller. So this bus is the 8-bit data bus, and this data bus, whenever you want to connect as a data to any one of the port 0 pin, you have to go through port 0 latch, okay, so, and also the port 0 driver. So if it is data, now timing and control can also want that, no, I don't want data, I want address to be coming over here, AD 0 to 7, right? So that means A0 to A7. You have to consider either A7 to A0, or you consider D7 to D0. Okay, so whether, but any one at a time. You cannot have both address and data simultaneously. Otherwise, that means there will be a burst condition or short circuit condition. So any one at a time, either data or address or port 0 function as input or output. Okay, assuming I want only address. So in that case, this port 0 latch will be disabled, rather the connection to the data bus will be disabled to the drivers. The driver will get the 8-bit input from this program address register. Okay, so this program address register will give the output 8-bit address, so that's why it is unidirectional. Okay, look at this bus, this is unidirectional 8-bit bus. So this will give address, 8-bit address, A7 to A0 over here, but this part of this program address register, this line is a 16-bit line. Okay, you have to remember this parts that I'm telling. How I remember, I never mocked up, and these are not written in the datasheet also. How I'm telling you, because based on the logic. So you have a 16-bit address line, A15 to, look at this, you have A15 to A8 and then A7 to A0. So there are 16 address lines. However, you just have 8 data lines, D7 to D0. Okay, so for address part, if you have a 16-bit program counter is a 16-bit, I told you in PC this is a 16-bit up counter, and then program address register is another 16-bit register. So certain registers are 16-bit here, like stack pointer also. Okay, so you have a 16-bit value here in this program address register. That 16-bit actually gets splitted into two 8 bits, A15 to A8 over here, because port 2 is multiplexed with A8, A15 to A8, and then A7 to A0 comes over here, which is going to the port 0 alternate function. And timing and control makes sure whenever address is coming to drivers, data should be stopped. Okay, so anyone, either address or data should come, or whatever is stored in the latch, so that should be updated. So in fact, the latch gets updated with the data value, so because it is inline or in series. So, but for address, the series element is this program address register. From, if you consider the program counter is storing the address that needs to be applied. Okay, but if you consider port 3 and port 1, so port 1 is connected to ISP port and port 3 is connected to this interrupt serial port and timer. Okay, so let's say over here also, let's verify that. So port 1 is connected to ISP port. So that's why mostly MISO and SCK, these are SPI programming lines, ISP programming lines, in system programming using SPI protocol. So this is multiplexed with MOSI, MISO and SCK. Whereas port 3 has interrupt, serial ports, and what else? Timers. So this is serial port, RxD, TXD. These are interrupts, INT 0 bar and INT 1 bar. And these are timers, okay, T0 and T1, external hardware timer inputs. In addition, there are some control lines also. Read and write bar are both control lines along with this EA, VPP, EA bar, VPP, ALE, program bar, and PSEN bar. Okay, so this three along with RD, WR bar and RD bar are the basically are the control lines, but certain control lines are only coming, like RD and WR bars are coming through port 3 only. So that's but interrupt, serial port, and timers are definitely present, as we have seen. Actually, all four categories are multiplexed with port 3. Okay, so any question? I will take attendance afterwards. Okay. Since you need to study a little more and then ask question, no problem. So let me note the attendance. I'll open the attendance file. I'll tell you certain things before we pack off today. So this is the attendance file that I download, and later on from the name search, we segregate as per roll numbers, and then we will compile the attendance at the last. So you can see the joining time. So like the person Anirudh Roy joined at 12:03 after I started the meeting. Obviously, some people were waiting. But later on, I can actually find out, you can see the timing, right? For everyone, I can see the timing. So who joined when. So some people joined at 12:19 and even, let's say, any other latecomers in the class. Someone joined, okay, someone has left the meeting. Okay, so from here, actually, I can see what is the timing and if you are joining and when you are leaving. Such as, look at this Mayur Manik Jaitonde. He has already left, so he's not listening, obviously. But I can easily find out when he joined and when he left. So it gives me this information, like Astitva Sharma. So he came at 12:16 and left at 12:16. So he just stayed here for less than 1 minute. So if I see such thing, I'm going to mark as absent. Okay.
No, sir. Sir, I came at 12. I came at 12 and then I left and then I joined again. I had some issue with the internet. Really sorry for that.
I just downloaded. I just downloaded.
I'm Optical Sharma,
right? So your attendance is showing up over here as per the latest information that MS team is giving. So you should be careful with your joining time. And
no, I just wanted to say that I'm still here.
Sorry?
Really sorry for that. I just say that I'm still here. I'm just really sorry for joining it.
I cannot understand what you're saying. Anyways, you can leave now, and people who wants to discuss, they can only stay back. Okay, so others may leave.
Thank you, sir.
Okay.